The x component of a net force acting on a 2 kilogram particle versus time is graphed below. We want to assume the particle starts out at rest, and let's see if we can find what this particle's acceleration must be as a function of time. So there's a relationship between force and acceleration, and that is Newton's second law that puts that into a mathematical relationship. And so Newton's second law is as follows. It's that the sum of all the vector forces acting on an object will equal the product of the mass of that object times the object's acceleration. It can also be written as F net, the little subscript net, equals ma. So in this problem, though, we just have one component of a force acting on a particle. This would be called the net force in the x direction. Because a net force could have multiple components like any other vector. They didn't talk about any other forces on this particle, so I just assume that it's the net force. All right, now what this vector equation implies is that the sum of the forces in the x direction will equal the mass times the acceleration in the x direction. And the sum of the forces in the y direction will equal the mass times the acceleration in the y direction. And even if we were to do a third dimension, which we can, the sum of the forces in the z direction would be the mass times the acceleration in the z direction. All right, so the one we want to focus on here then is actually this one for this problem. Because we have the force in the x direction, so we want to find the acceleration. As a graph, what it'll look like is this. We're going to start at the bottom with a force versus time graph. In this case, just to be very specific, it is the net force in the x direction. And they said the shape was like this. Okay, now what we want to do is we want to let that be the very bottom of our stack of motion graphs now. And we just want to put our acceleration above it. Now, the acceleration and the force will have the same shape, which makes that easy. And they are not like a derivative and antiderivative of each other, actually. They just have the mathematical relationship that the acceleration is the net force divided by mass. Then from there we could draw, velocity. And this is actually going to be, let's see, a case where the velocity would have a shape like this. It started from rest, they said, so we want to start right here with v equals 0. And this will be the x component of the velocity. And then there will be a position function, of course. Yeah, it didn't have any initial position or anything. So let's see, we'll have some kind of curve to it. But anyway, they're asking us for the exponent of the particle's acceleration. So all we want to do for that is just use the formula ax as a function of time will equal the net force as a function of time divided by the mass. So we're going to want to know what that function is. As you can see, the units on the left here are newtons, and over here we have seconds. So we should get a slope for that. I won't call it m though, because that's already reserved for the mass. I'll just call it k. So we want to go down 12 newtons and over 20 seconds. Negative 0.6 newtons per second. So, want to come up with a formula for this. As a function of time, it can be a linear function. I'll just use that little subscript of little zero, little knot, it's called. That can be the intercept. So negative 0.6 newtons per second t plus 12 newtons. Looks like that would be our linear equation for what the force is doing. So we just want to plug that in here. Let's divide by the mass of 2 kilograms. And let's see. I guess that's negative 0.3. And now we have to think of what the units would be, though. So a newton is defined as a kilogram meter per second squared. It's a mass times an acceleration. So if you do divide by kilograms, you end up with just meters per second squared. Notice that this is newtons per second, so there's another second down there. So this unit should actually be seconds to the third. And when you multiply by time, you'd get just meters per second squared, because time would be in seconds when you plug it in. And over here we have 6 meters per second squared. Yes, that would be good right there. All right, so it's a changing acceleration. Next, what is the x component of the particle's velocity as a function of time? So we would definitely want to integrate to find that now. So Vx as a function of t will be the antiderivative of Ax as a function of t dt. So I guess we would get it's going to be negative 0.15. It's tricky because you have to think about what the units should be and like how they should work out to be a velocity. Yeah, so I would keep those same units, of course. But when we multiply by t squared, that would be seconds squared, so it'll leave us with the units we need. Alright, so far so good. But we have to have a constant. We have to have a constant of integration. But the constant of integration would be the VI, and that would just be 0. Because they said it started out at rest. Alright, so that is that. I'll just erase that constant. We don't need it. And this is our velocity function. All right, well, next it asks for, let's see, the x component of the particle's displacement is a function of time. So we just want to integrate one more time. Delta x of t. Now this time, I'm going to do a definite integral. In a sense, I'm going to go from a t of 0 to some final time, which I'll call tf. The reason I do it that way is because for displacement, you should have a clearly defined start and end to the integral for the time interval. Alright, so we just want that. Okay, so gotta use my calculator on that one. Looks like negative 0.05 meters per second cubed t cubed plus 3 now. 3 meters per second squared t squared. Okay, and then we'll do plus a constant, which the constant's gonna cancel out anyways, like you don't even really need it. Some initial position, right? But then what we would do is put our limits in. And now we try to go through and evaluate it with the fundamental theorem of calculus. Plugging in our final time, you'll see that the XO will cancel no matter what XO is. Negative 0.05. I'll leave the units off for a minute. T final cubed plus 3 t final squared plus xo, right? But that's only part of it. Now you have to subtract plugging in the 0, which is just going to basically be 0 plus xo. So yeah, as you can see, the xo does not matter here. And we arrive at our final equation for the displacement then. Yeah, our final equation is going to be negative 0.05 meters per second cubed t cubed plus 3 meters per second squared t squared. Alright, and then just plug in the time that they requested. How far will it be located from its starting position? So just do a delta x of 20 seconds. Plug it in. If you put that in the calculator, it comes out to 800 meters.